let me introduce our speaker for tonight. We are extremely pleased to once again welcome Ron Frost, Professor Emeritus at the Department of Geology and Geophysics at the University of Wyoming. Ron got his bachelor's at the University of Virginia in 1969 and his master's at the University of Washington in 1971. He got his PhD, and all of these, of course, are in geology, his PhD from the University of Washington in 1973. And since then, his research has concentrated in several fields of petrology, and petrology is just another word for the study of rocks and how they form. And most specifically, he's been studying the geologic evolution of the Wyoming Province, geochemical aspects of serpentinization, the melting of ore bodies during metamorphism, geochemical classification of granite, and geochemical evolution of anorthosite and related rocks. So thank you, Ron, for coming. And I'm just going to start your slideshow here, and we'll be off to the races.
We hope.
Yeah, this is all good. This is going to be great. Okay, let's do this. Yep. It's going away. Okay, take it away, Ron.
Thank you. Thank you. This is, it's always a pleasure for me to come and talk to the geologists at Jackson Hole. I think it's my third or fourth time. And if you've seen some of the other talks, you'll probably see some repetition in this talk. A lot of us like to joke, particularly us who work in the Wyoming province, that Wyoming is the nucleus of North America, that everything else has been assembled around Wyoming. So I have the pleasure of telling you a story of 4 billion years of Earth history in an hour. See if we get there. Anybody know where this is? Yeah.
Fremont and Jackson Peak.
Okay, now. Okay. Works. Okay.
Yeah, let me try and get rid of this. Yeah. Oh, I want to go away completely. I don't know. Okay, let's try that.
Okay, so the core of North America is called Laurentia. And it's essentially the Precambrian rocks that underlie everything else in the interior. And it consists of 10 domains of Precambrian age. The guys in sort of reddish tones or pinkish tones are, hey guy, go back, are Archean, and the guys in the brownish greenish tones are Proterozoic. And you'll notice that there are 3 domains in here that have roots that go back to the earliest geologic history of the Earth. The Wyoming Province, the Slave Province, and the Nain. So we'll be talking about Wyoming. So here's a geologic map of the Wyoming Province. Sadly, a lot of the good rocks are covered up by dirt, but what I've coded here are the ages of the rocks in the various of the Laramide uplifts. And as I go through the talk, I'll explain the color coding. Now, one of the things about Wyoming, the reason why it's considered one of these ancient provinces, is it has a substantial population of rocks that formed between 3.0 and 3.5 billion years ago. One population is north of here in southwestern Montana, and the other population is located in central Wyoming in the Granite Mountains. Now, one thing about these original crustal rocks that we have is they don't look anything like modern granite batholiths that you would find in the Sierra Nevadas. They're very distinctly different. And the theory of how these Archean, or what should I say, Paleoarchean gneisses formed is based upon the assumption that they melted directly from ocean crust. And it's hard to make that happen unless you over-thicken the ocean crust. So the theory is that they form in, what should we say, oceanic plateaus, very much like some of the oceanic plateaus in the Southern Pacific. And as they got thick enough, the lower portions of the plateau started to melt. And then these melts got intruded to make granites. Now, these granites are not like the granites you'd expect to find, as I say, in the Sierra Nevadas or elsewhere in Wyoming even. They're very much richer in sodium than they are in potassium. The dense residua produced by these guys sink into the mantle, and this light granitic crust then floated above sea level, and this may be the time when we finally had continents forming. So these sodic granites, which are known to their friends as tonalites, are widespread in the Paleoarchean in the Wyoming Province. Here's a shot of the Granite Mountains, which contains the biggest block of these Paleoarchean rocks. The Granite Mountains are one of my favorite areas because they show you what Wyoming looked like before the mountains were rejuvenated. So the Granite Mountains have pieces of granite sticking up through flat-lying tertiary sediments. They haven't been excavated. So there's three rock types there. I mean, there's two major rock types. You got a tonalitic gneiss, which obviously you see is strongly foliated. It's this gray color that allows people to call them gray gneisses. And these are intruded by an orthogneiss. And by orthogneiss, I mean, you can tell that this was originally an igneous rock. It's just been a little bit tweaked around, so it's got some foliation and everything. Now, the interesting thing about these tonalite gneisses is when you separate out the zircons, I mean, this is the way we study these rocks, is we take out the zircons, we put them on a special analyzing instrument called the shrimp, and we hit them, these little, let's see, there we go, these little round circles are the points where we put the beams from the shrimp, and you get an age out of that particular portion of the rock, of the mineral. So you see some of these things have ages of 3.3, and some of them have ages of 3.8. So this particular rock contains evidence of zircons that formed at a much earlier age than the rock itself, and were entrained into the melt sometime during the formation of that rock. We call these xenocrysts in the fact that they formed someplace else, which is what xeno means. Now here's a diagram that takes a little bit of time to understand. We're dealing with isotopes of hafnium. Most of you probably haven't even heard of hafnium. Hafnium's in the same family as zirconium. Now, you have heard of cubic zirconia, right? So zirconium and hafnium are what we call high field space strength elements. And lutetium is what we call a rare earth element. And lutetium decays to an isotope of hafnium. This thing over here, called epsilon hafnium, is a measurement of how much of the hafnium in the rock is derived from the breakdown of lutetium, and how much of the hafnium in the rock is the original non-radiogenic hafnium. This is the hafnium ratio we get if you analyzed a chondrite, a meteorite. Okay. But over time, underneath there, hidden secretly, underneath this barrier, is age, going from 2.5, which is the end of the Precambrian, of the Archean, down to 4.5, which is the formation of the Earth. Now, in the mantle, in the depleted mantle, the lutetium breaks down slowly to form hafnium, and lutetium hafnium ratio increases like that. Let me see if I've got another cool. There we go. So that's the path to be followed from the mantle at any given time. So at any given date, such as this obvious date right here, you're going to have a lutetium hafnium ratio in the mantle of that. Any rock that is derived directly from the mantle will have that ratio. Mafic rocks have a lot more rare earth in them than the mantle, and therefore there's more lutetium to break down, and it forms, to follow a trend like that. And felsic rocks have even more rare earth, and the hafnium will evolve much faster, and it will follow a path like that. So that's some of the background you need to interpret this. Now, these are the hafnium ratios from various rocks in Wyoming, ranging from the stuff we see in the Wind Rivers at about 2.6, 2.7, to the rocks that we see right here, those zircons at 3.8. And the first thing you can see from this is none of these lie on the depleted mantle line. So all of these rocks in the Wyoming Craton that we've measured so far involve a mixture of mantle components plus a crustal melt component. The other thing is there's a whole bunch of these guys over here. These are from other localities. The black dots are from Australia, a place called the Jack Hills, where they've gotten all sorts of zircons out of rocks that are very, very old. And these green runs are from the Slave Province. And these rocks are way off of the trend, and they could follow a trend like this back to the very origin of the Earth. And we have those zircons I showed you have a trend that shows that the lutetium, the hafnium budget in them may well have been from the original crust of the Earth 4.5 billion years ago. And I think those are the three major places where we've got this on the Earth. This evidence of the Hadean crust. Now, these green dots come from the Slave Province. And the Slave Province, I pointed out to you, is way up north in Canada, around Great Slave Lake. And very similar to the Wyoming Province, it has really, really old rocks in places, much younger rocks in places, and a bunch of rocks which are probably closer to Proterozoic. And the interesting thing is that in the middle of the Slave Province is famous because it has huge gold mines at Yellowknife. And Yellowknife gold mines are found in a sequence of rocks that are 2.86 billion years old. And right here in the Granite Mountains, we have a sequence of rocks exactly like the stuff at Yellowknife that are 2.86 billion years old. So I would maintain that at one time, the Slave Province drifted away from Wyoming and wandered up north. So when I gave this talk in Canada and I told them that the Slave Province was a portion of the Wyoming Province that wandered away, they were not particularly pleased because they thought the Wyoming Province was a portion of the Slave Province that had wandered away. But Wyoming's in the middle and the slave is in the margin. So that's the reason why we say everything else was built around Wyoming. Now, at some point in Earth's history, and this is a big debate as to when it happened, plate tectonics began. And in plate tectonics is an oceanic lithosphere that's subducted underneath, who knows, continent, oceanic arc or something, and it melts to produce the things we see, you know, the andesites and stuff we see in the Cascades. And these things are associated with much higher potassium contents relative to sodium than the early granites. So there's a general transition from sodic granites to potassic granites over time in all of the Archean provinces. Wyoming makes that transition much earlier than some of the other provinces. Oops. So one of the key things about the Wyoming province, one of the things that makes it so worth studying, is it gives you inescapable evidence for when plate tectonics began. And there's several pieces of evidence. The most important piece of evidence is right here in the Northern Tetons. In the Northern Tetons, we have the best example of the earliest Himalayan orogeny on Earth. I mean, let's put it this way, the oldest preserved Himalayan orogeny on Earth. Because the Archean went through a bunch of traumatic things in its life. And some of the earliest high pressure rocks may well have melted and turned to something else. So over here, up in the Moose Basin area, metamorphism, the earliest metamorphism is very high pressure, okay, around 12 kilobars. This temperature here, which you can't see, is 900 degrees. This is an exceedingly high pressure and temperature, and it's very, very rare in the Archean. So if you go up to Moose Basin and you go up into Moose Basin, you see these great big blue kyanites in the rock. That's telling you about the high pressure metamorphism there. Now that took place, I said, about 2.69 billion years, 2.7 billion years ago. Up there, the rocks into which these things have been placed suffered another metamorphism at 2.68 billion years ago, which is about 7 kilobars, and you can see right here, it's about 750 degrees. That is a typical metamorphic conditions of a typical continental collision. If you look at the Alps, where the Alps have come together, the rocks there have been metamorphosed about that pressure. If you look at the Himalayas, the same sort of thing. And if you look at the Alps, you'll find in many places in the Alps, really high pressure rocks like this. They're always fragments that are been put together in this second lower pressure metamorphism. So this is one piece of evidence that says, oh, so this is just like the modern Himalayan type metamorphisms. See, the other thing is when the mountains are pushed together, when India got slid underneath Tibet, or when Italy, slammed into Europe, the rock gets really thick. And those thick rocks don't hold very well, and they slide apart. They open up. The hot rocks then get decompressed and they melt to make a very, very pale leucogranite like this. Leuco means light. And you can see these pieces of dike in here, they've been pulled apart. So this is evidence. This is from the Tetons. This is evidence that the rocks are being pulled apart, decompressed, and melting at about 2.684 billion years ago. So we have everything in the Tetons that we have in the Himalayas and in the Alps that tell us this was a continental collision that took place 2.68 million years ago. And this is the first evidence of that kind of collision any time on the Earth's history. Makes the Wyoming Province pretty cool. The other thing we have in the northern Bighorns and through most of the Beartooths and in the Wind Rivers are a series of granites. If I took you to the Bighorns, I dropped you in by helicopter, and you looked at the granite and got to know the granite really well, and then I took you to the Sierra Nevadas and you looked at the granite, they look exactly the same, particularly in the Bighorns, which even though it's older, about 2.8 billion years old, it has not been deformed at all in 2.8 billion. So the compositions of the granites that I'm pointing out here are identical to the compositions of granites you find in the modern Sierra Nevada. They were formed by plate tectonic processes. Okay, and let's see what we got here. And then finally, in the history of the Wyoming Province, are these blue things. There's the northern Tetons, but those high pressure rocks in the northern Tetons were accreted to the rest of the Tetons along a fault called the Moran Fault at 2.62. And this contains a whole bunch of different terrains that smashed into Wyoming about 2.62 billion years ago, which is a process of accretion that's very, very similar to what we see from plate tectonics today. And the last thing that took place in the Archean in Wyoming was a series of granites that run across the southern Wind River Range, across the Granite Mountains and the Laramie Range that all have essentially the same age of 2.62 to 2.63. These were essentially stitched Wyoming together to make the Wyoming Craton. So this is the Wyoming Craton as we see it now. But if you go out down here and you look at the detailed geologic maps here, you'll see about 10% of the Laramie Range there is made up of dikes, big mafic dikes. And those dikes were emplaced when the southern part of Wyoming, whatever was down here, rifted away at about 1.8 billion years ago. And when it rifted, there's an ocean there. And against the ocean, there's a very nice sand beach, which now is represented as the Madison Peak quartzite. It's not at all sure where the fragment that's missing from Wyoming went. It was 1.8 billion years ago. The Earth does a whole lot of things in 1.8 billion years. It may have, some people say that it's the Superior Province in Ontario. The only problem with that is that the geologic history of the Superior Province does not at all look like a Wyoming province. So I just say it just disappeared. The Madison Peak quartzite is typical Shurer facies sandstone with cross bedding, rare conglomerate horizons. Here, see these pebbles? These are pretty big pebbles, but most of the time you just see a quartzite, essentially a sandy beach that's been metamorphosed to green schist facies or so. It was tilted to vertical here we can see the vertical bedding. It's going up like this. It's tilted to vertical about 1.8 billion years ago when Colorado rudely smashed into Wyoming. All of the Colorado province, in fact, all the way down to through New Mexico, the rocks are 1.8 billion years old or younger. There's no Archean down there. This was only one event during this period of time between 1.7 and 1.8 billion years ago when Laurentia was put together. Okay, here's our Wyoming province. We've already talked about the Slave. There's accretion onto the Slave province, the Superior, the Wyoming, and these guys all smashed together along this big thing called the Trans-Hudson orogeny. And by 1.8 billion years ago, the Laurentia, the core of North America that we know it, was assembled and established. At the same time, we'll get to this later, over in Europe, the assembly was forming the core of what we call Baltica, which is the European version of Laurentia. So here we are, all assembled. This is Laurentia. There's a massive igneous event that took place 1.4 to 1.5 billion years ago. Made voluminous anorthosites that extend all the way across eastern Canada, and lots of very iron-rich plutons, which extend all across North America. The only anorthosite outside of Canada, well, there's another anorthosite over here in California, is the Laramie anorthosite. And associated with the Laramie anorthosite is the Shurer granite. So it avoided Laramie, the Wyoming province, for a good reason. Wyoming province is an old, very stable crust. So the Laramie anorthosite was placed along the boundary between Wyoming province and Colorado, and the Shurer granite came up along with it. Now, these granites are very different from anything you'll see in the Wind Rivers, the Tetons, the Sierra Nevadas. They're very, very iron rich, which gives us this brownish color. They're very, very potassic, which gives it, the pink feldspars. I find it very fascinating that rocks of this composition, which are really, really rare, occur on the northwest corner and the southeast corner of Wyoming. One of them formed at 1.4 billion years ago, and the other one's forming today at Yellowstone. The Yellowstone lavas, excuse me, the Yellowstone lavas, if you go down 7 kilometers into Yellowstone, this is what you see. These rocks formed at 7 kilometer depth. This is the kind of thing that we're forming at Yellowstone today, these very, very distinct granites. Okay, so we formed Laurentia. And now what happens is these events called the Wilson cycles. J. Chusler Wilson sort of postulated that the history of oceans start out as rifting, and then the rifting would stop and the continents would come back together again and collide and make mountains. And he got that from eastern North America. This yellow banded thing here, excuse me, is a Grenville orogeny. Right here, along the face of this thrust fault, we have pressures 12 kilobars or so, probably very much like the stuff we have in the Tetons. And the Grenville formed about 1 billion years ago when Baltica, remember I talked about Baltica, that's Europe today. Baltica slammed in to North America to make the Grenville. And then shortly afterwards, well, geologic time, Baltica rifted away again. And then between 325 and 250 million years ago, it came back as Europe and smacked into North America. It had some friends though. The Wachitas were formed, well, down here is South America. Wachitas were probably formed by South America slamming into North America. But we have this band of rocks now, which all the way across here, they're added during the Appalachian orogeny. And then in the Triassic time, Europe rifted away and drifted over to where it is now. Something similar was happening on the west in part of North America between the Jurassic and the Paleocene. So 100 to 50 million years ago. And this was interesting in the fact that there wasn't a continent that slammed into here. It was a bunch of island arcs. So if you can visualize what Southeast Asia looks like today, you got India, you got China, and you got Taiwan, and you have Borneo, and you have you even got Australia, but you have a whole bunch of little island arcs apart from the continent. You got the Philippines. And if you take all those things and slam them into the continent, you'd make what we have in the Cordillera today. And of course, when the Cordillera slammed in, or the island arc slammed in, it made the Laramide orogeny. So the mountains we see today in the wind rivers and stuff like that were produced by this collisional event. So all this other stuff here is stuff that's been stuck on about the Paleocene. Yeah, I like to say, if you want to summarize the geologic history of North America, you got the Wyoming Craton, which is the nucleus of North America. Colorado slammed in about 1.8, and California is an afterthought. So after everything was put together, North America is trying to fall apart or trying to be torn apart, okay? So the key thing here is destruction, not accretion. Well, that's not very well focused, is it? So out underneath, well, out in the middle of the Atlantic, for example, you have the Mid-Atlantic Ridge, and North America and Europe are spreading apart. Now, in the Pacific, it's called the East Pacific Rise because it comes around through the Southern Pacific and it comes up in the Eastern Pacific and it comes up right through here. About 8 billion years ago, North America rode over the top of the East Pacific Rise. So we had all this heat coming up underneath North America. So here's the East Pacific Rise going up the Gulf of California. And that had a very traumatic effect on the poor continent. It led to the opening of the Gulf of California. So the Gulf of California here is directly because the East Pacific Rise is coming in to rift. And what happens in the East Pacific Rise? Well, one thing that happens to it is it becomes the San Andreas Fault. The San Andreas Fault is a big fault because it's part of the whole tectonic framework of the world, right? So East Pacific Rise comes in here, becomes a San Andreas Fault, and then it becomes the spreading centers out there in the Pacific. Won the Fruka rise. Okay, but it's more than that. It led to the formation of the Basin Range. If you've ever driven across Nevada, you know, it has a bunch of little peaks and valleys and peaks and valleys. That stuff used to be all connected, and it's been pulled apart as from the effects of the East Pacific rise. Now, if Denver existed 8 million years ago, and San Francisco existed 8 million years ago, they would have been 200 kilometers closer than they are now. So they've been pulled apart. This big expansion has taken place because of the effect of the East Pacific rise. And the other thing it did is it led to the rejuvenation of the Rocky Mountains. If you heat anything up, what happens to it? It expands. So if you heat a big wad of the mantle up, it's going to expand. And the Rocky Mountains pretty much eroded away by about 6 or 8 million years ago. They're like the pictures I showed you of the Granite Mountains with little peaks sticking up out of the tertiary. And when the other part got heated up, the Rocky Mountains rose approximately 3 kilometers. You know, you can figure that out, but Denver is at 5,000 feet. You go up to Canada and you look at Calgary, which is about the same place relative to the mountain range, it's about 1,000 feet. That difference in elevation between Denver and Calgary is probably the amount that the whole Rocky Mountains went up because of this heating from underneath. And I think that's it. But we have lots of time for questions. There we go. Got a question?
Yeah, how does the Mount Owen quartz monzonite fit into the
Mount Owen's quartz monzonite is 2.54 billion years old. It's one of the last things to take place in North America. Can we get, one of the last things to take place in Wyoming, can we get back to the slideshow?
Yeah.
Okay. There it is. So. So let's go back to this map, okay? About on the north end of the Wyoming Craton. Well, let's go back to another map. Shows it better. The northern end of the Wyoming Craton, up in here, these rocks are very complex because they have an Archean component, and then or a 2.8 component, and then they have a series of rocks which are running like this that are 2.5 billion years old. This is a shear zone there. And I postulate that these things were being subducted and melted and emplaced as the Mount Owen. So it's a later, it's totally undeformed, but it came in as a result of a collisionary event someplace in Montana.
Brent, if you can hear me, if you have any questions from the Zoom audience, could you read one of those?
Oh, we're taking questions in the middle. I did not know that. Okay, yes, I
Or
do.
No, I'm sorry,
It's
the
over.
main presentation is actually over.
Okay,
So we're in the Q&A period.
sorry,
That's okay.
my bad. I stepped away for a moment. We do have a question from Mike Shurer. He asks, how much of the basin and range extension is due to over thickening of the crust?
The basin and range, Mike, is got two extensional events. When the Rocky Mountains formed, I mean, when the Laramide orogeny took place, there was a lot of stacking in where Nevada is now. So the rocks were very much over thickened, just like they do in the Himalayas. When they're over thickened, they extend. And so if you go out and you look at places like the Ruby Range and stuff, you'll see extensional fabrics that are later overprinted by the extensional fabrics of the extension due to essentially the most recent extension. So there are two distinct periods of extension in at least the Ruby Mountains. One of them related to the over thickening and maybe delamination related to the Laramide orogeny, and one related to the overriding of the East Pacific Rise.
Okay, I have another question from Mike. Are there ophiolites in the Tetons? And if so, where can we go find them?
There are, unfortunately, we, I don't have a map in there, but in the Moose Basin region, there's fragmented ophiolites. There's ultramafic bodies that are lying parallel to the foliations of the rocks. They contain gabbros. They contain, well, metaperidocites now. There's no serpentinite. But those are related to essentially the collision that formed the high pressure metamorphism. But yes, there are ophiolites in the Tetons, but they're very, very fragmented.
Okay, another question from Mike. Can you describe the suture zone in the Tetons?
The suture, there's two. Okay, in the Moose Basin, which is a great big synform, on the top of the core of the synform, you have these really, really high pressure rocks, and they're sutured to the lower pressure rocks along fabrics that have been totally overprinted by those extensional granites. So the picture I showed of the leucogranite with the extensional bands in it, that's essentially where the suture there is. The suture between the Moose Basin rocks and the rocks of the rest of the Tetons is a massive shear zone that runs from about Bivouac Peak over the backside of the Moran, and I don't know how far you can trace it south before it gets essentially obliterated by the Mount Owen. But it's just a major shear zone.
Okay, I have one more from Nan. I'm not sure I got this right. Have there been any geophysical surveys of the Wyoming province that have provided or not provided that information?
There's a paper coming out. I don't know the journal. My co-author Carol Frost is the co-author. She did the geology part, the geophysicists at the USGS did the geophysical part that essentially does the most modern geophysical analysis of the Craton. So there have been, and it's probably being published this year.
So maybe we could take some questions now from the audience.
When you go into Moose Basin, it seems you see a lot of evidence of stretching, like with the Budanage but you also see incredible folding. And are they from the same time or are they?
The
totally
folding event
separate?
is first.
So let's repeat the
Oh.
question.
Okay. So you're Beverly, right? So Beverly asked whether the extensional events, which I showed in my, that image of the granites, and the folding events that she has seen up there are part of the same thing. And the answer is, in my opinion, no. The folding events are about the same age as the high pressure metamorphism. So if you map the folds, there's always amphibolite or mafic rock in the middle. And then there's the politic rock on the outside. And in the very, very core of the folds, the mafic rock is still in very, very high pressure metamorphism. The extensional stuff is seen in the big sheets of granite that intrude it. And these are little dikes that were in the granites that were being emplaced as that whole thing was being torn apart.
And that came later,
That came later.
but they're so close.
Yeah,
They're physically close.
they're physically very close, exactly. But those granite rocks are always away from the amphibolite. So if you go into the middle of Moose Basin, you get in that amphibolite politic terrain, there's no, the granitic rocks are not there. If you go to the east, you get into this big band of what we call the Webb Canyon gneiss, then you'll find these extended dikes in there.
John?
Kind of two-part question. First is, can you describe how the easiest or best way to get into this space?
There isn't any.
So the question was what's the,
The question was, what's the easiest way to get into Moose Basin? I've gotten in there from the east side and I've gotten in there from the west. From the east side, you have to get across the lake and then you have to hike in Webb Canyon or various other trails. They're not easy trails and it's, you get up high enough and I think you lose the trails mostly. From the west side, it's about an 8-mile walk in and a substantial climb, but there is no easy way in.
And this is all north of Moran, right?
It's all north of Moran.
Now, the second question, you talked about that chart we had, where you talked about the M1, M2. You said M1 was quite unusual. So I thought you said big blue piece of it.
Right. So the question is, M1 appears to be quite unusual. And M1 is, M stands for metamorphism and 1 stands for the earliest. And the thing about M1 is there are places around the world which you get that high pressure. It's very, very rare in the Precambrian to have rocks that high pressure. So that's why I was saying that they're rare. And you know, the first time I walked up there and saw the giant kyanites, I said, this is a very, very special place. And it is. It is one of the most important places in studying the tectonic evolution of North America.
So how do you generate the really high pressures? Very deep collision?
Very deep collision. So what you see in these collisions, okay, so let's envision that we've got a subduction zone now. We've got some sediments coming in. Here's a continent over here. What you see is if you go to the Alps where it's really well exposed, you'll see big fragments, big blocks hiding in these schists that are really high pressure. And they probably underwent high pressure at some depth and then were being brought up tectonically at the time they collided. So it's not, the collision event that we see in the Tetons was probably 750 degrees, 7 kilobars, 750 degrees. The high pressure metamorphism probably took place at much greater depth, a little earlier than that during a subduction. That's what we see in the Himalayas, the Alps specifically, and that's how we interpret it. I mean, the amazing thing to me is that in this teeny tiny fragment of rocks that we have exposed in the Tetons, it actually picked up that event that we can study. But, you know, unlike the Alps, we can walk for miles and miles and miles on it. It's a very small fragment. So we have to use our interpretation from modern geology to try to understand that earlier tectonics.
Basically, you put all that together and say that plate tectonics was clearly going at about 2.8.
Yeah, that was
question.
2.7.
Question.
Oh, well, if you put that all together, he says, you can clearly say that plate tectonics was operating at 2.8 billion. The interesting thing is that in some places around the world, some cratons, plate tectonics doesn't really start until 2.5. In the North China Craton, for example, they have primitive, those sort of tonalites and everything, all the way up to 2.5 billion years ago. Wyoming is one of the earliest. I think in the Barberton Land Craton, they get stuff that might be taking place about 3. But so the transition from that early Archean type of formation of rocks to plate tectonics is diachronous. In order to have plate tectonics, you have to have a craton. The older the craton, the earlier the plate tectonics are seen. The younger the craton, the younger the plate tectonics. So it was a process that was going on around the Earth in different times because of the different types of continental blocks that were floating around.
Where was the place that you said was about 3?
In South Africa.
Was what?
Oh, what was the place that was around 3? And that was South Africa.
I understand how you can estimate the age of the rocks, isotope ratios. How do you estimate the pressure under which they were formed?
The question is, how do you estimate the pressure under which rocks formed? Well, that's a good question, because I really didn't go into it in great detail. But the minerals tell you the pressure. The minerals in a rock have a certain pressure, temperature, stability field. And they're forming assemblages that have specific temperature, pressure fields. So by looking at the minerals at Moose Basin, we could say these minerals here in this assemblage could not have formed at any lower pressure than, let's say, 12 kilobars. So it's the whole field of what we call phase equilibrium.
I think you called the rocks in this basin exotic, and it's like going into a geology place, so you can see it. In the Granite Mountains, is it spectacular and dramatic there?
Question.
So Beverly asked, is the geology in the Granite Mountains as spectacular as that in Moose Basin? And my answer is, it depends upon your appreciation for rocks. In fact, I could take people up to Moose Basin, even though it's a very difficult walk, and they'd be totally unimpressed. Oh yeah, the rocks, and there's some little blue things in them. The same thing is in the Granite Mountains. It's a lot more subtle there, but the rocks are impressive because of their age and a lot of their relationships. Because a lot of the key, it's interesting, a lot of the key to the study of the Wyoming Craton lies in the Granite Mountains. That's where we get these really old zircons and stuff like that. But, you know, you'd walk around, or some people walk around and say, yeah, that's a gray rock. It's got some stripies in it. I mean, so yeah, my feeling is in everything in science, the more you understand it, the more excited you get about it, right? I mean, I can't be very excited about genetic stuff, but I bet you if I knew more about it, then I got involved in it, then it'd be more exciting. So it's just a question of understanding what you're looking at.
But Moose Basin area, Webb Canyon, you don't need to understand everything. You can look at it like an artist.
Yeah, they're fabulous rocks.
Yeah.
Yeah.
Question?
I'm visiting from Idaho, so I was wondering, are the granites in the Wyoming province, are they related at all to the granites down in southern Idaho that you know of? Down like City of Rocks area, or are they just, were those accreted onto it?
So the question is, how is the Wyoming stuff related to the rocks in southern Idaho? And I think that those things are much, much younger.
Because if I'm remembering correctly, I thought like City of Rocks was like 2.5 billion.
There is some evidence, I think it was in the Ruby Mountains,
Okay.
of 2.5 billion year old gneisses.
Okay.
But those rocks in the rubies have had a long, torturous life with a lot of granites that came in much later. So I think this is the same true with the Idaho stuff, is that there are a mixture of granites of different ages in there because, you know, the very good thing for us as scientists is nothing much happened in Wyoming after 2.5 billion years ago. But you get over into the basin and range, and there's a lot of magmatism went on, and that obliterates a lot of stuff. They may make you some interesting rocks to study, but you know, you're studying them in terms of the Mesozoic ages as opposed to the Archean ages.
So if the Granite Mountains are somewhat related to the slave blocks, should we expect to be able to find gold?
You know, the one
Let's repeat the
unit.
question.
Oh, if the Granite Mountains are related to the slave, can we find gold in the Granite Mountains? Well, there's gold at South Pass. And the South Pass rocks are essentially the same sort of stuff. The units that we correlate with the slave are little snippets. You know, the whole outcrop might be the size of this room, but it might have the whole sequence of the stratigraphy of the slave going from pillar basalts on one side to gray lacquers on the other. So the interesting thing about the Wyoming province is it doesn't contain many what we call greenstone belts. So a lot of Archean provinces are extremely rich in ore, and the Wyoming province is extremely not rich in ore. And that's because it's dominated by granites and gneisses rather than greenstone belts. Which is just why, you know, I always say, you know, it's a good thing that they didn't find lots and lots of gold in the Wind Rivers, because there'd be roads all through the Wind Rivers looking for gold. Yeah. Any other questions?
There's some questions from the Zoom audience, if you're ready.
Oh, yeah.
Okay.
Thought we depleted the Zoom audience. Go ahead, Brent.
No, they keep coming. Okay, the first one, Kent would like to know how the intrusion of the Rendezvous Mountain metagabbro fits into this story.
Well, you know a little bit about the geology. Rendezvous Mountain is a very interesting gabbro. I mean, one of the things about it is it's the same age, 2.69, as the high pressure metamorphism, Moose Basin. And it's really solid evidence that they were in two different places at that time, because there's no high pressure metamorphism in Rendezvous Mountain. There are evidences across the Wyoming province of mafic rocks intruded about that time. But how it fits into the rest of the story is not really clear because it's just one block.
Okay, thank you. Another question, did you work out the timing and process for forming the bright-eyed gneiss in Death Canyon?
We're working on it. We went up and sampled it a couple of years ago with a colleague who does geochronology from University of New Brunswick, and he's still working on it. I mean, it's complex, as you might expect, because everything in the Archean is complex. But how it fits in, I don't know. Maybe we will learn.
Can you describe the process for forming bright-eyed gneiss?
Oh, well.
How's that different?
The major process for forming granite gneiss is deformation at high temperatures. And we're talking about temperatures probably in the range of 600, 700 degrees. So granite isn't melting yet, but at high temperatures and moderately high pressures, quartz particularly flows like butter. Quartz looks like a very, very strong mineral, but it deforms very readily at temperatures above 450 degrees or so, and it just slides. When the quartz is sliding, the feldspars are going along with it, and when they deform, they make bands, and those bands are what make the granite into a gneiss.
Can you just maybe describe for folks who aren't familiar with what bright-eyed gneiss is, what it looks like, and what the mineralogy is?
The bright-eyed gneiss is a gneiss that lives up, is it Death Canyon?
Yeah.
Yeah, it lives up Death Canyon. And it was named by, not too sure, it may have been Dave Love. What it has is little crystals of magnetite surrounded by a halo of feldspar in a sort of a gray gneiss. And it was called bright-eyed because of the fact that in the sun, you can see these sparkling magnetites. Now, mineral biotite is compositionally the same as magnetite plus K feldspar. So my feeling has always been this thing was getting really hot, pushing really high grades of metamorphism. And the biotite started to break down to make magnetite and K feldspar, and that's what made the eyes. The process is still something that we're working on. Any other questions? Well, I had a good time. I hope you guys did. Thank you, Cynthia. It worked.
It did, thank goodness. So thank you, Ron. And on the behalf of the geologists of Jackson Hole, I'd like to give you a little card.
Oh, thank you.
Let's move over here so we can both be in the
Oh.
camera here together.
Well, there we are.
Yeah. And then also a little present. And so we know that you probably avidly collect igneous and metamorphic rocks. So this is something a little different.
Oh, uh-oh. Oh, wow. Oh, those are cool. I was looking at these at John's house. This is it's a sediment with, I don't know what it is, but it's got some really great sedimentary features. And yeah, that's cool.
It's actually a sandstone
Right.
from near Kanab, Utah, from the early Triassic. And it's got some iron oxide had moved through the the sandstone and preferentially
Painted the grains.
coated some of the grains so you can see some of the sedimentary features much more clearly. So
Thank you.
you're
I
very welcome.
appreciate that.
And
So-
thanks from the Zoom audience. You had a thanks from Wisconsin, well worth listening. And we all appreciated your talk as well. Thank you.
Thank you, Brent, for the Zoom meistership.
So here's that.